The goal is to create a DNS request in Common Lisp and send it to a DNS server. But first of all, what is DNS? Every host connected to a network is identified by an IP address to reach the host we are interested in. But it's difficult to remember, so we assign a symbolic name to the servers. But then we need a way to convert it to the actual IP address. Every computer can manage its own list of association. For example, in Linux it is the file /etc/hosts. Nevertheless, nowadays it would be impossible to keep the list of all the websites updated on every host. This is the reason why we use a distributed database, the DNS. We don't really need a lot of details about how DNS works, but an idea on the record is useful. Inside DNS, each record has at least the following fields: a name, which is the actual domain name, a type, which can assume a lot of values, but the most common one are A, which means that inside the value we will have the actual IP address, or NS, which means that inside the value we have the address of a server that has more details about the IP address. The value, we have discussed it with the type. DNS is an extensible protocol, but the core is defined inside the RFC 1034 and 1035. We will look at them during the discussion of the implementation. The DNS protocol is based on UDP, and the packet is the same for the request and the response. We start by implementing the request. We will need a /babel, which is used to convert string into octets, and usocket. We will need it to send a request to the network. Then we have a classical configuration for SPCL during development. QClasses and QTypes are two parameters for the questions. A and NS are the type we discussed before. Their values are described inside the RFC. We can see that A is 1 and NS is 2. Other common types are CNAME and MX for males, but for the purpose of the exercise, A and NS are sufficient. In means we are using the internet network. Then we have a class which describes the field we can find inside a DNS packet. Again, we can find all of them inside the RFC. I've copied all of the values, but we won't use all of them. The ID is just an identifier for the current packet. The server will reply with the same ID we have provided to the request. QR can be 0 or 1 depending if this packet is a request or a response. Then for opcode AA, TC, RD, RA and RCode, for the moment we can use all the default values. Finally, we have the list of questions and the list of answers. To create a request, we just need to fill the list of questions. So, below we have another class with all the properties of a question. Again, we can find them inside the RFC. QName is the name of the domain we are asking for. QType is the kind of question we are asking. It could be A, NS, and so on. And then we have QClass that for us will always be in. For the encoding, we have a function encode, which takes as input a DNS packet. It creates an array, a buffer of bytes. And then we have the function extend vector, which takes a packet and concatenates all of the values inside the buffer. Extend vector is a generic function because we will have an extend vector for a DNS packet, but also for a DNS question. The array will start with an initial dimension of 4096 bytes, but the field pointer is 0, so at the beginning it is actually as it has 0 elements. Then we will use a lot the function vector push extends, which inserts a new element inside the vector and increments the field pointer. Push short is a small utility we will use a lot every time we want to add a 2-byte number to the vector. To add a 2-byte number, we start by shifting to the right of 8 bits. This way we push the most significant byte, and then with a bitwise end we push the less significant byte. This is enough to start writing the extend vector for the DNS packet. So we use def method because extend vector is a generic function, and in particular the first parameter, pkt, has to be a DNS packet. To understand the following code, we have to look at this image. Every line are 2 bytes. The first byte are the first 8 bits, and second bytes are the other. We can see that ID takes 2 bytes. So we use push short the ID inside the buffer. Then we have to put QR of code AA, TC and RD inside the third byte. QR is the most significant byte, and this is the code that we need. If QR is a response, so the value of the first bit is 1. If it is a request, is 0. Thus, if it is a response to this byte, we have to add at least 128. And we can do this in this line. Then we go on summing all the other values if the bits are sets. For example, the opcode is a number. In our case, is always 0, but it could be different from 0. We have to add it in the middle, so we shift by 3 bits and we add the numerical value, and this is the role of hash. Then we have AA, TC and RD, which are 3 bits, and so we sum 4, 2 or 1 depending on if they are set or not. This is basically the conversion of a binary value to a decimal value. And this is probably the most difficult part in implementing the DNS. If it is clear, all the rest is implemented exactly the same way. For example, the 4th byte, we can see that Z is always 0. RA is the most significant bit, and so we sum 128 if it is set. Then our code is again a number, and its position is already in the less significant bits. So we can sum the value as it is. With this code, we have filled the first 2 lines. Then we have the number of questions, the number of answers, and more details that we don't really need for the moment. But those are just the length of the properties inside the class pkt. In particular, all of them are 2 bytes long. And so we use again the push short function. We push the size of question, answer, NS and RS. This way we have finished the implementation of the header. Immediately after the header we have questions and answer, NS and additional sections. Since we are implementing the request, for the moment we don't need this part. We can just implement the question. As we can see, we have some for loops, and then we use again the extend vector function. It may look like recursion, but we are not actually calling the same function, because the first argument, Q, R, NS and RR, are not DNS packet. For example, Q is a question, and so immediately after we have extend vector for a question, which is basically the encoding of this packet. So we start with the name. In our case, the name will be a list of all the labels without the dot. We just had to split with respect to the dot. Otherwise, in particular, the protocol says that we have to write the length of each label. For example, google.com has two labels, Google and com. So for each label, Google, we have to put the length, 6, and then the actual value, Google. Then 3, com. Finally, we end with the byte 0. And this is what we are doing here. We iterate over all the QNames, this list. For each, we create an octet from the string. We push the length, which is at most 1 byte. More specifically, it can be at most 63. And then for each label, we push, and then we have to append the encoded string. We push 1 byte at a time. We end with the 0 byte, and then we still have to put qtype and qclass. Qtype and qclass are two keywords, and the actual value we have to put inside the packet is given by the parameter we have defined at the beginning, which are described by the RFC. They are a list, so we can use the function assoc to read the actual tuple, and then with coder we take just the second element and we push them as short. I haven't defined the class, then the question, and now I can define the method. Now, how can we try this code since we don't have the decoding? We will use Wireshark. Wireshark is a program that listens to all the packages which are in ingress and in egress inside our computer and show them to us. So we will send the packet, and so we will see one line inside Wireshark, and then immediately after we will see the response. The request we want to send is this one. So its ID is 257, which can be any number. We will see the same value in the response. It's a request. And then we have the list of questions. In particular, we have a single question for google.com. We will send this request to 8.8.8.8, which is a DNS of Google. Let's try it. First of all, I start Wireshark. Inside the filter, I add a constraint to just show the packet which contains the IP address 8.8.8.8. Otherwise, we would see a lot of packets. And now I can send the request. As you can see, the first one is the request from my PC to 8.8.8.8, which is a request with ID 101 in hexadecimal, a request for A, so an IP address of google.com. And inside the response, we can see that the IP address is this one. For today, this is all. Let me know in the comments if you like the video, leave a like and subscribe.